In this presentation, Yul Tompton and I are going to convince you that the surface composition of inhalation powders is important to know and that it is in fact knowable. Don't think too deeply, think superficially. The surface is where the particles touch. Inhalation particles are small, the surface to volume ratio is high, so there's a lot of surface to touch. The surface is not simply the particle outline and its rugosity. The chemical composition of the surface is an important factor in the aggregation, deaggregation that we need in inhalation powders. The surface is not what one thinks, one must analyze. Lactose is not simply lactose. Let's take the case of lactose. Is there lactose on respiratose? Yes, there is some. So in the blue here, we have the lactose signal in blue, and there's places that are quite blue that are relatively pure lactose surfaces. Other surfaces have odd nitrogen-containing molecules that we have detected in TOF-SIMS that I'll say a little bit more about in a bit. And we have some areas that are very strong in sodium. Others are high in potassium, so high that you don't see the lactose signal from underneath. In other cases, you see potassium cationized lactose ions. The blends that I'm going to talk about are these blends. They're binary blends of respiratose SV003 with drugs and with coating agents, and then some tertiary blends that have these binary blends with drugs plus added 8% lactose fines. Let's talk about multivariate image creation using TOF-SIMS images or TOF-SIMS data. TOF-SIMS is basically a surface mass spectrometry technique, and here are some examples of spectra of the ions that are of interest in this section about coating agents and lactose. So here's leucine and magnesium stearate and PROVE, and then lactose here. And so we have different spectra. These are generally fragmentation spectra, but we do get molecular ions, in this case, molecular ions cationized by sodium and potassium in the case of lactose. Let's look at what we get if we do a univariate image of this lactose particle with leucine coated onto it. If we take the leucine peak, the strong leucine peak that we saw here, and we there's the grayscale image of it and the 365 peak, that is the lactose plus sodium, and we make that red and make that green, then we get this kind of orangish image here. But if we take the whole spectrum of both the leucine and the lactose and then fit each one of the pixels, because each one of the pixels has a spectrum behind it, we fit each one of those pixels to this whole spectrum, you could say, then we get much better contrast, so we can see the leucine on the mountaintops and the valleys not yet of the respiratose not yet coated with leucine. Coating agents on respiratose, let's go to that now. In general, for this set, we have PROVE, magnesium stearate, and leucine coated for 5, 15, and 25 minutes with a diosina high shear mixer. We see some things that, okay, this is pretty well coated already. It doesn't seem like it changed very much in the degree of coating, maybe even goes down a little bit. Here it looks like it goes up some, gets redder, which means more coating agent. Here it gets redder, which means more coating agent, but not as red as here. So that's summarized here, where this should have been blue, but in the cut and paste became some other color, but it has its blue error bars here. This is TOF-SIMS result. Percent coverage with magnesium stearate, and it compares to this XPS result with magnesium stearate, and you see that it's lower, and this would be expected because XPS, which is X-ray photoelectron spectroscopy, while TOF-SIMS is time of flight secondary ion mass spectrometry. And in TOF-SIMS case, we have a primary ion coming in and secondary ions going out and being mass analyzed, while in the XPS case, we have an X-ray coming in and electrons coming out, and the energy of which tells you what atoms you have on the surface. But the analytical depth for XPS is deeper than for the TOF-SIMS. So if you have a thin layer that looks like very complete by TOF-SIMS, it could still show the underlying substrate because the XPS is seen through it. And that's what we have with the case of PROVE. PROVE are the red ones here, and you see this big difference between the TOF-SIMS solid line and the PROVE XPS dotted line. Well, the XPS for leucine and the TOF-SIMS for leucine are very similar, and the TOF-SIMS for magnesium stearate and the XPS for magnesium stearate are very similar. So PROVE is a very thin coating by comparison. We also have now the other set, which is quantifying the compositional distribution of APIs on respiratoes. And here, the surprising thing is that we're coating respiratoes with SBS as if it were a coating agent almost. So very high levels of coating. The difference between these up here and these down here are that these are showing the topographical variation that you get in total signal in SIMS, and this is normalizing away that topographical variation. We can look at quantifying the spatial resolution. I already said we can see the changes in the composition, and we can quantify that the same way we did with the coating agents, but we can also quantify something about the homogeneity. One way is just looking at the histograms, and so for something that's homogeneously coated as this is, you'll have a thin full width at half max for your histogram peak, and for something that's not, you'll have a broader one. This one we kind of thought of when we first looked at it in here, looked like, okay, you got red spots on green, but this area in the center is not perfectly green, and you see you do have still some drug signal from the interior, the areas between the spots, and that's what, but you're getting something on the way towards a bimodal distribution here, where you have both signal for the bright spots and dark signal for the dark places. So here's the bright spots and here's the darker areas. And then with the much more diffuse and smeared out image here, you get a more smeared out broad peak. I can also say that you can put numbers on these by talking about the skewedness. This one's skewed right, this one's skewed right. You can talk about the peakedness, how much wing signal there is compared to the peak. And you can talk about the entropy, how random it is. It would be very random if all of them had this similar area here, similar intensity, so it was a very gray image. Finally, let's look at a different sort of quantification of the distribution on the surface that actually retains the pixel to pixel information. And here we retain no such information. This is just statistical distribution of values, not the distribution on the surface and where it actually is. If we look at 2% drugs on respiratoes, which look like the squares here, so that would be those squares, and those squares, we see in this so-called skeleton area that we separate these three. The skeleton area is just a way of saying how many pixels are together that are the same. And so you could make a square here of pixels that were all the same intensity, and then you draw the X in that square, and the pixels that it takes to draw the X is what the skeleton area is. And so if you had a completely red square here, it would just take two long X lines, and that would be very low skeleton area. And you get a very low skeleton area here. But here and here you have smaller areas, and so many more little rectangles to draw the diagonals of, and you get higher skeleton areas. What's surprising here, and this is surprising because it shows things you can't really easily pick out from the images. It shows that the budesonide, these green squares over here, the one in the middle has the highest skeleton area, and that's because of that signal that's in between the pixels here. So finally, here's the summary. And for inhalation powders, I've demonstrated the things I wanted to demonstrate, interesting results for PROVE, and the coating of salt butymol sulfate. And thank you.